On April 28, 2021, NASA's Parker Solar Probe made history, becoming the first spacecraft to touch the sun, plunging straight into its outer atmosphere, the corona. Fast forward to Christmas Eve 2024, and Parker smashed its own record, zooming closer than any spacecraft before at a staggering 430,000 miles per hour, making it the fastest human-made object in history. The data it collected will revolutionize our understanding of the sun for decades. But a big question remains: how did Parker survive? To answer, we need to dive into the sun's fiery layers. Unlike a planet, the sun has no solid surface. It's a massive ball of hot, ionized gas plasma. The layer we see, the photosphere, ranges from 4,000 to 6,500 degrees Celsius. Above it, the chromosphere climbs to 30 degrees Celsius, and then comes the corona, the outermost layer where Parker flew at temperatures of 2 to 3 million C. Strangely, the corona is hotter than the surface, defying our intuition that things cool as you move away from a heat source. Here's the trick: low density. Imagine putting your hand into a 200 degrees Celsius oven without touching anything. You don't burn immediately because the air doesn't carry much heat. The corona works the same way. Its particles are moving insanely fast, but there aren't enough of them to transfer massive heat energy. Parker's heat shield only had to withstand 400 degrees Celsius, far below the millions outside, but still hot enough to melt most metals. So how does Parker survive such extreme conditions? Engineers used 3 brilliant strategies: the heat shield thermal protection system, TPS, a 2.3-meter wide, 11.5 cm thick carbon-carbon composite shield, protects the spacecraft. It can handle temperatures above 20 degrees Celsius, thanks to a foam core that blocks heat and a reflective white ceramic coating that bounces the sun's energy away. Inside, Parker stays at a comfy 30 degrees Celsius. Instrument placement. Most instruments are tucked behind the shield. Only 2 must face the sun directly, carefully engineered to withstand the extreme heat to collect critical data. Advanced materials and design. Carbon-carbon composite, heat-resistant coatings, and clever insulation work together to manage the intense radiation and thermal stress, keeping Parker intact as it dances through the sun's outer atmosphere. Parker isn't just surviving, it's thriving in an environment hotter than molten lava, faster than anything humanity has ever built, and closer to the sun than anyone dared to imagine. The data it sends back promises to unlock the sun's deepest secrets and revolutionize solar science, even as we marvel at Parker. It's a reminder: engineering at the edge of the impossible is what makes progress happen, whether in space or in life. The Kanban view turns tasks into draggable sticky notes, letting you move them through stages with ease. The Gantt chart provides a bird's-eye view of who's working on what and makes assigning tasks simple. The list view allows batch updates, and the chatter feature in each task lets you send emails, add log notes, and schedule activities like meetings, calls, or to-dos. No more digging through endless emails. Everything is clear, organized, and accessible. Collaboration is seamless. Tag colleagues, attach files, and track progress in real time. Big projects are easy to manage with tasks, deadlines, and milestones set in just a few clicks. And the best part? Ado lets you manage projects for free. Forever Your First app is free for life, with unlimited hosting support. Check the link in the description to take full control and manage projects like a pro. Now, back to Parker Solar Probe, the first critical instrument. Fields studies the sun's electric and magnetic fields, mapping how energy moves through the corona. Its long, thin antennae, about 2 meters each, extend beyond the heat shield, directly interacting with the sun's charged particles. Made from titanium and heat-resistant materials, these antennae operate without active cooling. The second instrument, a solar probe cup, SPC measures solar wind speed, density, and temperature by capturing charged particles. To function, it must face the sun directly. Constructed from high-melting metals like tungsten, molybdenum, and niobium, it withstands intense heat without damage. Another key engineering feat is Parker's cooling system. While most instruments remain behind the heat shield, solar panels exposed to the sun use pressurized deionized water to absorb and transfer heat. The water moves excess heat to a radiator in the shield's shadow, then cycles back, keeping the panels functional. They can also retract partially at close approach to minimize exposure. Sensors across the spacecraft ensure instruments stay behind the shield. If sunlight is detected, an automated alert triggers real-time adjustments. This self-governing system is critical for Parker's safety, especially given the vast distance and harsh environment. Parker has already made historic discoveries. In 2018, it found switchback sudden zigzags in solar wind that could explain why the corona is so hot and how solar wind accelerates. It also identified the Alphen critical surface, where solar gravity stops controlling the wind and it flows freely into space. Parker discovered a dust-free zone 3.5 million miles from the sun, where particles vaporized due to extreme heat and captured the Venus dust ring, providing insight into how dust moves through the solar system. The probe has also improved space weather understanding, tracking solar energetic particles that can disrupt satellites and power grids on Earth. Each discovery reveals new facets of the sun's behavior, showing us our star like never before. Parker Solar Probe isn't just surviving. It's thriving in an environment hotter than molten lava, faster than anything built by humans, and closer to the sun than anyone ever imagined. Each data point brings us closer to unraveling the sun's deepest mysteries and revolutionizing our understanding of the solar system.